taking you back to kind of stoichiometry. So that's 1-4 kind of takes you into a little bit of stoic. Okay. I think I did include 1-4 in your packet though, so I think we're okay there. All right. So we end up having 2 or more pure substances. Those 2 or more pure substances are your elements and compounds. They're going to be combined to form a mixture. And that composition can vary. So that mixture can be analyzed to figure out what each component is. And you can either use stoich to convert those masses to find the original amount in the mixture. You can also sometimes analyze the mixture using mass spec. We'll talk about that in a couple minutes. So an elemental analysis to determine the composition can be qualitative or quantitative. And when you do that, that is part of this analytical chemistry. So if you get into college, you can actually take a course in analytical chemistry. The elemental analysis is going to, like I said, have a couple of different ways to do this. You can do a combustion analysis where you drive off, you combust some of the material. So like a carbon containing compound is going to be converted into carbon dioxide. The hydrogen is converted into water, and you can measure how much carbon dioxide is driven off and how much water is driven off. And then the nitrogen is converted to nitrogen monoxide or nitrogen dioxide and sulfur, and then further converted into sulfur dioxide. You can also use spectroscopy, which is optical, where we pass light through, and we'll use the Beer-Lambert law to do that. We'll get into that later on this year. You actually do a couple labs with the spec devices that we have where you're using this Beer-Lambert law. You can use mass spec, which we talked about last week in terms of 1.2. And then there's photoelectron spectroscopy, which we will get into in 1.7 in the next coming days. All right, so let's get into a couple of the kind of activities here. First of all, you always have to start with a balanced equation. So they want us to balance the equation. They gave us the equation up here. You need to make sure it's balanced. Now, oftentimes, not always, but oftentimes, you will end up having a balanced equation. I don't think I'm sharing my screen here. Hold on a second. Sharing my screen. Hold on. Sorry, guys. Just want to make sure that I am sharing the screen. I am. They've changed the way that the stuff looks on here. They've changed the way that the stuff looks, and so I'm not as familiar with it. All right, so anyway, let's get back to the equation. Most of the time in AP, they will have already balanced the equation, but it's always a good thing to kind of double check. In this case, they haven't, and they've even told you, hey, go back and balance the thing, so they've kind of reminded you. So you're going to have Al plus O2. They are not usually very big sticklers on your states of matter on here either. So that's not a big deal to kind of worry about unless they say specifically like identify the precipitate. And then you would have to make sure, if there were multiple things here, you'd have to make sure that you identify the precipitate in that particular thing. They're not usually going to make you do that without giving you something pretty easy. Like, if there was another thing over here that was like CO2, that would be pretty obvious that that's a gas, or H2O. They're not going to give you some obscure thing. I'm eventually going to have you memorize some solubility things. There's only like 4 that you have to memorize, which isn't bad. So as long as you can memorize the cations or anions, those 4 that never precipitate, then that would be another example of where that would be. But we're getting ahead of ourselves at this point. Okay, so let's balance this equation. You need to have oxygens. Remember, even and odd, what do we do? Double the odds. So we're going to double the, oops, that That's just not pretty. Try that again. We're going to double the odd here. Okay, that's going to give us 6 oxygens, and it's going to give us 4 aluminum. Okay. All right. So what mass of oxygen was in the sample? Well, what we need to do is we need to see what happened here. So when they had this sample, it was a mixture of aluminum and aluminum oxide. It was weighing 120.91 grams. They're analyzed, and the total mass of the aluminum in the sample was found to be this. Okay. So if we know that the aluminum was this amount, that's the mass that we started out with here. And we know that in the end, we ended up with this amount for our, that we started with, then the difference between these would have been the oxygen, right? Okay. So we're going to subtract this guy from this guy. So for B, so this is A, for B, and you want to try to make sure that you're delineating your steps for people. So 120.91 minus 120.32. Okay, this is the aluminum mixture, and this is the aluminum that was left over in the end, or that, I'm sorry, the aluminum that we started with. The aluminum in the sample was found to be this. So if this is the mixture and this is the aluminum, the difference is going to be your oxygen. So that's going to be 0. Yeah, it's just this thing. Sometimes I put this down and then it makes this huge line going up, and so it's a little frustrating. Okay, 59 grams of oxygen. Okay, now if that's my oxygen, okay, I'm going to take this, and this I'm going to create a BCA table for. Remember our BCA tables? Okay. So I need to convert this into moles first. So I have that many grams of oxygen. Remember that 32.0 grams of O2 equals 1 mole of O2. That's going to give me my moles of O2. So 0.59 divided by 32, I get 0.018. How many sig figs? 5 sig figs. Wow. 4. So that's 3.38. And that's moles of oxygen. Okay. I can use my ratios here. For every 3 moles of this, okay, for every 3 moles of this, I have 2 moles of this. Everybody see that? So I can set that up in stoich if I want to. Sorry, my lines are not very steady and straight. So for every 3 moles of O2, I have 2 moles of Al2O3. And then if I want to keep that going, in 1 mole of Al2O3, I have how many grams? 101.95 grams. I don't know why this is being naughty today. All right. So then that'll give me my grams of Al. So that ends up being 1 point. So I've got this times 2 times 101.95 divided by 3. I got 1.2, and I'm just going to come up here and give my answer because I ran out of room over here. Hopefully you guys have a little more. I need 5 sig figs for my answer. So 2, 5, 3, 1 grams of Al2O3. All right, everybody comfortable with that stoic? Yes, sir.
Can you use that instead of the BCA table?
You can, yeah, absolutely. Yeah. Once you understand the BCA table, I think this comes to, kind of more naturally. But if you wanted to do the BCA table, I'm going to erase this stuff just to get it out of my way here. You could certainly do the BCA table and come up with the same amounts. Okay, because you would have your BCA. This would be your moles here of your oxygen, so 0.018438, and then take that up into the cloud and then divide back down, and you come up with the ratio of moles over here, and then multiply that by this, and then that gets you your answer the same. Okay. Mass percent, if we talk mass percent, then that is part over the whole. So they want to know the part of the aluminum oxide versus the mixture that we started with. So we take our amount of our aluminum oxide that we have here, which we have determined to be 1.2531 grams, and we're going to divide that by that original mixture, which is 120.91 times 100, and that ends up being 1.1% for our percent mass. Oh, stoichiometry, mass percent, all kinds of cobwebs. Yes, sir.
12.531 instead of 1.35.
120.91 times 100. So you put 1.25.
Oh no, I'm going back to C.
Oh, C here.
Yeah, I have this one point.
Okay.
And I just use the BCA.
So we had our 0.59 divided by 32. So we had this as 0.0184375. I divide that by 3, and then I multiply it by 2. So 0.01229.
Oh, never mind. Yep, it's coming in.
Okay. All right.
Oh, I see. I forgot to have the 0 in front of point.
Okay.
0.
All right. So we got it taken care of. Everybody good? Good? Everybody happy? Thumbs up, thumbs down? Don't have a clue what I'm doing. Talk to me. Okay. All right. So then the we do, I'm going to skip that. You guys can go and watch the video if you need to. Remember, you can call up the answer key, click on the scan me, and it'll call up the video for you on that. If we have time, we'll come back to it. All right. Atomic structure, electron configuration. So we have our atoms made up of these protons and neutrons. Those are in our nucleus, remember? And then we have our electrons. Remember, the electrons really are what kind of give us pretty much our range of reactivity, because remember, it's how they bond and how they form to be able to fill those electron shells up. So it's really the electrons that we spend most of our time on, and how many we have in those outer shells. Those outer shells then we can look at all of them we can look at in terms of electron configuration. And you guys did this, if you remember back, the 1s2, 2s2, 2p6, remember that whole thing? Okay. Schrodinger, the guy with the cat, if you do science jokes at all, Yeah, he's the dude with the cat. He said that we can obtain 4 quantum numbers, L or NL, M1, S. We just called these N, L, M, and S when we did them in class. They describe the probable location of electrons. The inner electrons are called the core electrons, and then the outer ones are called the valence electrons. You'll remember this chart from way back when, where we had the principal number, the quantum number. So this is how far it is from the nucleus. This is the shape of the orbital, the SPDF. And then we had that magnetic quantum number and then the spin number. The quantum numbers, you do not need to know how to do them for the AP exam, okay? But they're a good kind of refresher to remind where we come from when we get into the electron configuration. So we have these orbitals. We have the s orbital and we have the p orbital. Remember, the s orbital is a spherical orbital. The p orbital is kind of a peanut shape. And then we have hybrid orbitals that we'll get into in our next unit, where we kind of mesh these together and make sp orbitals. But we're not there yet. Cart before the horse. We can arrange these so that we have our s orbital here. We have a p orbital this direction, and this direction. Remember, we're talking about these in terms of a 3D model in a 2D representation right now. So you have to be able to kind of visualize this. Our s orbitals then can fit where we have these different levels. You can kind of see where they get cut away here. And then for each orbital, there's a possible number of electrons. For the first energy level, there's only 2. For the second energy level, there's a total of 8. For the third, 18, and for the fourth, 32. This looks complicated, but if you use the periodic table instead of a complicated chart like this that I had to use when I was in chemistry, then it becomes much easier to be able to determine your electron configuration. Coulomb's law then, which you have an activity in your packet that you're going to be doing in terms of Coulomb's law, tells us about the force between the charged particles. It's proportional to the product of the 2 charges and inversely proportional to the squared radius. So in other words, the closer you bring 2 things together, the more the charge is going to interact. So if you have 2 magnets that are the same, like south and south, the closer you get them together, the harder it is to push them together. You've tried to do that before, right? Okay. But if they're opposite charges, the closer you bring them together, the more that attraction occurs. So distance is a factor for it. And then quantity of charge. If you have a really strong magnet, it's going to like pull things together. And you've probably seen, like, I don't know, there's probably, I think there's some movies out there like Marvel Universe or something like that, where they have like a, you know, a bracelet or something on, and then they get pulled into a magnet or something. I can't remember what movie that was. Okay, there we go. Okay, here we go. See, somebody knew. I knew somebody would. But they've got all this metal on, and then they get pulled into this, you know. What's the other one? Eureka. If you've ever watched the series Eureka, it's kind of a little dated, but they have the same experience on theirs. Anyway, so Coulomb's law. Rules for electron configuration. Again, remember that with electron configuration, if you use your periodic table, life is easy. Okay? So when we look at this in terms of this, this is your 1s. And when we actually did this in class, we had you guys pull this guy over to here. Okay? We keep him over here because he's a noble gas, and most of the time it works over here. But for electron configuration, we're going to want to think of helium over here. And it follows through in numeric order. So here's your 1s, your 2s, your 2p, and then however many electrons. So if we're going to oxygen, we would do 1s, 2, because there'd be 2 of them, 2s, 2, 2p, 1, 2, 3, 4. Remember how to do that? And then it just follows through in numeric order. They're never going to give you some weird hokey thing down here, so don't worry about those. All right, this tells you the distance from the nucleus, this tells you the subshell, and this tells you each electron in the subshell. So electron configuration for nitrogen is 1s2, 2s2, 2p3. If you add up these superscripts, it's going to tell you the number of electrons. So 2 plus 2 plus 3 is 7. Nitrogen's atomic number is 7. Okay? So it's a good way to kind of go back and double check your work and make sure that your work is correct. Orbital diagrams then. If you have an S, it gets 1 blank. If you have a P, it gets 3 blanks. D's get 5 and F's get 7. And if you go back to your periodic table, that helps you remember because this would be 1 because there would be 2 electrons in that. You have 1, 2, 3, and then it doubles up again. So there's just 3 here. So however many boxes there are, divide by 2. So for the P, if you take 6 divided by 2, that's how many blanks you're going to need for your P level. For D, there's 10 across here. So 10 divided by 2 is 5. There's 14 here, so that's 7. So that's how they get these 7 blanks. All right, remember you can't double up until you've got them spread out evenly. So 2, 4, so this is nitrogen again. So here's your 1s2, so this is hydrogen, helium. This is lithium, boron, or beryllium, sorry, beryllium. This is your boron, carbon, and nitrogen. You can't double up until you've got 1 in each space. You also need to make sure that your spins are the same. So this would be an up, up, up. You wouldn't do an up, down, up. You wouldn't go down until you've doubled up. Make sense? There's also noble gas shortcut configuration where you go back to the previous noble gas. So for example, if we were to do cobalt here, we would take that back to the previous noble gas. We would put argon in parentheses, and then you start down here. 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. So 3d7. And then you don't have to write all that stuff out in the beginning. So here, this becomes this. So this is calcium. So this part takes place of all that stuff in the beginning. Easy enough? You remember how to do those? For the AP exam, unless it specifically says write out the complete electron configuration, noble gas is accepted. So unless they come out and say verbatim, write out the whole complete thing, noble gas is fine. Right? And you don't want to spend time writing the whole thing out if you don't have to. Because A, it's a waste of time, and B, if you goof it somewhere along the way, it's wrong. And you're much less likely to goof just a short thing than a really long thing. All right, so write the ground state configuration for arsenic, and then we'll talk about what ground state means here in just a minute. I get out at 25. I've still got time. Boxes of matches? So underneath the coffee pot, like one of the top drawers to the left, there's a whole bunch in there.
I know, I'm like
Yeah. I know, it's a lot. And if you didn't have me, you know, things are a little bit, you know, just come in for a different teacher. We'll get you there. If you need to come in for extra help, okay. And I'll get my answer keys up for everything after during 5,000 probably. I think my answer keys help, right?
Yeah, especially if I don't know if it's more than like a 4.2.
Yeah.
I don't remember this. I don't remember this. I remember the pluses and minuses. I don't know what that's minus one.
Yeah, I don't know that in regular chem that we covered this. So that's why we're going to talk about this one next. Okay. We talked about what a calcium ion is, but I don't think that we talked about it in terms of electron configuration. Okay. So don't get wigged out on this one. This is the one that I want you to try for right now. Okay. Now, this said ground state configuration of arsenic. It didn't say anything about complete. So that means that we can find arsenic on here, which is right here. And I can go back to a noble gas because they didn't say complete. They just said ground state. Okay. So if you wrote out the rest, it would be 1s2, 2s2, 2p6, 3s2, 3p6. And then I'm going to start with argon. And then yours would end up going 4s2, 3d10, and then 4p, and it's going to be 3. Okay? So again, I didn't write all that extra stuff out. I started back here at this previous noble gas. All right? Now, when they talk in terms of ground state, that means that the electron is not excited. It hasn't been energized in any fashion. Remember, when these electrons get energized, they move up levels. Okay? So sometimes you will have these move up different levels. So for example, this 2 here might get excited. Okay, these electrons might get excited and move up to here. They're always going to move out of the s orbitals and move up before they would move out of the 3d orbital. Because remember, this is further out than this guy. So in terms of our levels, we have 1, 2, 3, then we have 4. Even though they don't fill in that order, the 4s and 4p are still out here further than the 3d. So when an electron is going to jump or get lost, it's going to get lost from these outer levels first. Okay? So in terms of calcium here, when they were talking about the next one, they asked for the ground state configuration for calcium. Okay, I'm going to write down the whole electron configuration for calcium, and I'll explain why in just a minute. 1s2, so don't write this down because it's not going to be the correct answer to start with. Okay, I'm going to do a little bit of explanation with it. 1s2, 2s2, sorry for the straight up line, 2p6, 3s2, 3p6, 4s2. That is my calcium here, right? Okay. Now remember what a 2+ charge is. What have we done to get a 2+ charge? Taken away 2 electrons. So if we take away 2 electrons from there to give that a plus charge, this is where those 2 electrons would come from because that is the outer shell. So this is going to be our calcium 2+ for the electron configuration. That also happens to be the electron configuration for argon as well. Because remember what these, and I'm anthropomorphizing, I think is the English term for it. I'm not an English person, so don't call me on that one. But I do a lot of analogies, okay? and I'm going to personify, I think that's the word for it. I'm going to personify this. That calcium wants to get rid of those 2 electrons because it wants to look like argon. If it looks like argon, it has a filled outer energy level and it's stable. So by losing those 2 electrons, it does. Now, is it argon at that point? No. Why?
Protons?
Yes, exactly. It still has the same amount of protons. So it's still calcium. Remember, the identity of these atoms is based on the number of protons. That's what gives its identity, is the number of protons. Its electrons have changed, so its bonding is going to change and that sort of thing. But it's still calcium. It has the same electron configuration as argon, but it's not argon. Good? All right. All right, so questions on electron configuration?
No.
Okay. So this is probably the first, if you didn't have me for pre-AP last year or the year before, this is probably the first new stuff you'll actually have. Although I think we might have actually covered this in pre-AP, to be honest with you. All right, photon electron spectroscopy. This is easy, by the way. Super easy. If you can count to 6, you're good. Okay? So this is an experimental technique. It's going to measure the relative energies of the electrons, and it's used to create these graphs. These graphs then will directly correspond to the electron configuration. So the PES graphs, again, correspond to the electron configuration. This is sodium down here, okay? Now, this is called binding energy or ionization energy down here. This is how strongly these atoms are going to hold on to their electrons. The further away the electrons are from that central nucleus, the easier it is to pull those electrons away. It's going to take less energy. So if you look at this guy right here, this is a much smaller number than this number here, because the electrons that are further away from the nucleus are going to require less energy to pull away. Back in the day, when I explained this to my level 1 kids, I always talk about how as you move away from the nucleus, it's like moving away from mom. So you're a newborn, that mom is holding on to that baby like no tomorrow, right? Like nobody's getting that baby away from her, okay? Then you start to toddle around and she's holding your hand. It's a little easier to pull that kid away from mom. And then by the time, you get down to where you're at, where you're driving and you're further away, it's even easier to pull you away. But you're more responsible, so it's okay. And then by the time you go off to college or get your first job and you move out, it's even easier to pull you away. Okay, it's kind of the same idea, the amount of energy required. So when you get these graphs, and this is very sneaky of them, you've got to pay attention, okay? Sometimes they will have this x-axis flipped around. So pay attention. Make sure that if you're labeling this, that whatever has the most energy, that's going to be your 1s electrons. Okay. Then here, this is your 2s electrons. This is your 2p. And then we follow that up with 3s. And you can see here that the distance is between these is growing. These guys are in the same level, so they're going to be kind of tighter together. And then we have a jump in distance again because it takes less energy to pull these away. The corresponding height of this indicates how many electrons. So this peak here is half of what this peak would be, and it's 1/6 of what this peak would be. Does that make sense? Okay. So you can derive the electron configuration from one of these graphs. This would be 1s2, 2s2, because it goes up 2 here. This would be 2p6, and then finally 3s1. And then you can go to your periodic table and figure out, hey, this is sodium. And I think I did do these in pre-AP, if you had me. All right, again, be careful on these because they will reverse that x-axis, so pay attention to that on the AP exam. That's a very common thing that I've seen them do. All right. Here we've got this, and we are trying to figure out which element is represented by this spectra down here. Okay, this is my, so this is, again, this is reversed. Okay, this is where they reverse this. See that? So this is kind of going to be down here. You kind of imagine that. 52.6. And they have a 2 here. So imagine that's kicked out over here even further. Okay. So this is where they reverse that axis. And they will do it to you. You got to pay attention. Okay. And if you saw the first hiccup here as a 4, that should be your first indicator that this is backwards. Because if it was forward, that first indicator could only be at 2. Does that make sense? Because the 1s can only have 2 electrons in it. You could only have 2 electrons in any s. So this is going to be 1s2. That's this guy right here. Then we have 2s2. That's this guy right here. And then we have 2p4. So this guy ends up being oxygen. All right, see if you can figure this guy out. Yeah.
What was the strong number does it take away from the like, you know what I'm saying? Like, if you have, like, when
Okay, take me back to where we're at now.
So, you're looking at an element and you're wondering if it were to become an ion, would it take away its electrons or gain electrons?
Okay. Okay, I got it. So let me go back to a periodic table here because it's easier to explain there. So what he asked for those of you playing at home is how do we know if it's going to become a cation or an anion, essentially. Okay, so remember that things that are over on this side of the periodic table, these guys over here have 1 electron to lose in their outer energy level, and they're going to look like the previous noble gas. So these are going to tend to form +1 charges. These guys need to lose 2 electrons. So they're going to lose 2, and then they're going to look like the previous noble gas. When we get over to here, if they lose 3, like aluminum has a +3 charge, gallium does. If they lose 3, then they look like the previous noble gas. When we get here, they don't tend to lose or gain. They tend to share. And so these tend to be more involved in covalent bonding. Then we kind of flip. This is where it flips.
Excuse this interruption, just a little reminder, students, as you leave for lunch, we have some weather coming in and you need to watch the weather and be careful. Not sure exactly what's coming, but it looks like some thunderstorms, so be careful in your driving.
Got it. Okay. So we've got here, if these gain 1 electron, become 1 negative, they look like this. These gain 2 electrons. These gain 3 electrons. Okay? All right. Getting back to our last problem that we had over here. This is going to be our 1s2. This then going down here is going to be 2s2. Don't pack up on me. 2p6. I still have 3 minutes. This is going to be 3S2, and this is going to be 3P1. So we go over to our handy dandy periodic table. 3P1 is aluminum. Okay? So tonight, I would like you to do 1, 4, 1, 5, 1, 6, but you don't have to do the Coulomb's law one. Okay? So the Coulomb law is the longer one that looks like this. Okay? You don't have to do that one tonight, but I want the other 3, try to do the other 3 tonight. I will try to get the answer keys and the video uploaded to Google Classroom next hour.
Is there a reason why on the periodic table that you handed out, that there's no names on it?
Because that is the one, the periodic table that is on there is the one that you will be using for the AP exam. That's what they give you. And so because of that, I want you to get used to it.